Welcome to the next part of previous problem. Now the so far we have completed the displacement analysis. In the present case, the two unknowns are there, or two degrees of static indeterminacy, or two redundancies are there. So the matrix will be of 2 by 2 size, and the coefficient of a flexibility matrix are shown here. So they are 1 1 2 1. So these are the first coefficient or of a first column. Then the 1 2 and 2 2, these are the coefficient for the second column of a matrix. So let calculate the first column's coefficient. So F11, now when we say F11, the first number is 1 and second number is also 1. So you have to consider first two column, small m1 and small m2 for the flexibility coefficient calculation or flexibility matrix. Now here is a F11, so take m1 into m1 divided by ei into dx, integrating from 0 to L. Now consider all zone. Now let's see the first zone. For first zone, the limit is 0 to 3. So and values are x, or value is x. So m1 into m1 become x into x divided by ei into dx, and limit is 0 to 3. Second zone is 0 to 2, or limit. These are the limit. Then the zone is bd, and the value is 3. So 3 into 3 divided by ei into dx. And last zone is dA zone, and limits are 2 to 4. So limits for integration 2 to 4, and the value is 3. So 3 into 3 divided by ei into dx. So by simplifying, we have F11 is equal to 45 divided by ei. Now let's find out next value or coefficient of a matrix. F12 is equal to F21. Now these are the diagonal elements, so they will be same. Integrating from 0 to L. Now first number here is 1 and second number is 2. So we have to take m1 into m2 divided by ei, integrating from 0 to L into dx. Now consider first zone. First zone is a CB, and the limit for same 0 to 3, but the value of m2 is 0. So when we do the m1 into m2, we will get 0. So let's move toward the next zone, BD zone, and limit it 0 to 2, and the values are 3 into minus x divided by ei into dx. Then the next zone is DA zone, and the limits are 2 to 4, 2 to 4, and the values are 3 into minus x divided by ei into dx, and by simplifying we have minus 24 by ei. Now next coefficient F22. Now here the numbers are 2 2, so we have to take m2 into m2 divided by ei into dx, integrating 0 to L. First zone is CB, but the value of m2 is 0, so 0 into 0 becomes 0. So next zone is BD, and limits are 0 to 2, 0 to 2, and the value for m2 is minus x. So m2 into m2 means minus x into minus x divided by ei into dx. And next is dA, and limits are 2 to 4, and the value is minus x into minus x divided by ei into dx. By simplifying, we have F22 21.34 divided by ei. So putting in here and taking 1 upon ei outside, we have the flexibility matrix. The column for the first column is 45 and minus 24, and second column of a matrix is minus 24 and 21.34. Now, uh, let consider the compatibility equation or flexibility equation. dq is equal to dql plus f into q. Now, dq, the value for dq1 and dq2 are 0. There is no any displacement in the direction of the redundant. So already calculated in a previous lecture. And dql, the values are like this: minus 1903.125, and second is 1233.34, taking 1 upon ei outside, plus 1 upon ei 45 and 24, and the second column is minus 24 and 21.34 into the unknowns q1 and q2. So by simplifying, taking this or 1 upon ei will get cancelled, and taking this dql toward the left hand side, we have one simplified form. And then by solving, first row is 45 into q1 plus minus 24 into q2 is equal to 1903.125 is the first equation. Second will be a minus 24 into q1 plus 21.34 into q2 is equal to minus 1233.34. This one is the second equation. By simplifying, we have q1 and q2. By simplifying this above this equation, uh, q1 is 28.64 kilonewton, and q2 is nothing but the sc is equal to minus 24.56 kilonewton. So minus sign is there, so that means whatever the sign we assume initially, that is not correct. We have to make a change. We assume the q2 toward the, I think, right hand side, so we make it toward the left hand side. Now the let here you see the SC, we make it correct toward the for BC, FBD of a BC member. uh, the SC is acting, initially it is acting toward the right hand side. We, after the minus sign, we have make it correct toward the left hand side. SC is equal to my 25.56 kilonewton, and VC we having upward, and this and is equal to 28.64 kilonewton. Now the at B, at C there is a hinge support, so only one unknown will be there, HC and BC. Now at B, there will be three unknown. Let us assume their direction toward the HB toward the B, and VB toward the upward direction, and the moment will be a moment at B will be in a anti-clockwise direction, that means positive. Now let take a moment about B. Let take moment about B. So moment about B, the first one is a MBC, which is acting uh, anti-clockwise as per our assumption. So positive MBC plus uh, the moment of this 28.64 about this B, it will be 20 in a in a in a anti-clockwise sense. So my plus 28.64 into 3, and the moment of this point load, uh, that means the moment of UDL 25 kilonewton per meter. So point load will be 25 into 3. So 25 into 3, and lever arm will be half, so 1.5, and it will rotate about in a clockwise sense. So minus 25 into 3 into 1.5 is equal to 0. By simplifying, we have MBC. Moment of HB and VB will be 0 because they are passing through this point B. So their moment about B will be 0. So the by simplifying, MBC is equal to 26.58 kilonewton meter. Now next is let calculate the VB. To calculate VB, let do the summation Fy. Upward is positive, downward is negative sign. VB plus VB minus plus VB, then there is uh, point load at C plus 28.64 and the UDL minus 25 into 3. So by simplifying, we are having a VB is equal to 46.34 kilonewton upward. Also by doing the summation effects here for the above member, we having HB minus 25.56. What are the forces acting here? So by doing summation fx toward the right side positive and toward the left minus, two forces are there, axial forces plus hb and minus 25.56 is equal to 0. So we having hb is equal to 25.56 kilonewton. Now let's consider this column. For the column, now what are the forces acting at B for the BC uh, beam? The HB and VB acting up, and the moment at B is anti-clockwise. So same magnitude forces will be act toward the at point B for the column BA of the same magnitude, but they will act in the opposite direction. So to maintain the equilibrium, so in view of that, we keep all the forces, whatever we find out for from the beam here, and the unknown at A, let's consider MAB, anti-clockwise positive, HA toward the left hand side and V in upward direction. Let's take a moment. Now the point load is there at the mid span, 50 kilonewton point load is there over the column BA. Let's take moment about A. The first one is 26.58 kilonewton point load, sorry, 26.58 kilonewton moment is there in a clockwise sense, so it will be minus, make it minus 26.58. Then the point load 25.56 into lever arm is 4, so it will be rotated in anti-clockwise direction, so positive. The next one is uh, now this 46.36 passing through the A point, so moment will be 0. The next is moment at A, MAB anti-clockwise, so positive. Then the moment created by the 50 kilonewton point load in a anti-clockwise clockwise sense, so minus 50 into lever arm is 2 into 2 is equal to 0. By simplifying, we have the MAB is equal to 24.34 kilonewton meter. So these are the moment. Now let's draw the before drawing the FBD, shear force diagram. Let we having the now let calculate the HA. So to calculate HA, let consider the summation effects toward the right positive and toward the left negative side. So first is HA itself minus HA, then the next horizontal force is 25.56 minus 25.56, and next horizontal is 50 kilonewton over the column, so plus 50 is equal to 0. So we have HA 24.18 kilonewton. Okay, so after knowing all reactions, let's draw the shear force diagram. Now at C, the shear force or the reaction is upward is 28.64, so go up in upward direction, and there is a UDL, so UDL is of 25 kilonewton per meter, and so point load you have to take, so 25 into 3, so 28.64 minus 25 into 3. So by doing so, we having 46.36, and the line will be inclined line due to the UDL. Then the next is at A there is a reaction of 24.18 kilonewton, 24.18 kilonewton. So and therefore the 24.44 kilonewton at A, the reaction is it 24.4, and then the no load up to 50, so straight line, and there is a 50, so minus 50, so 24.44 minus 50 become 25.56, and no load between 50 and B kilonewton, B point, so there will be straight line. So we having a shear force diagram. Now next is a bending moment diagram. So at A there is a bending moment of 24.44 kilonewton meter, and to draw that you have to keep your pen over the member here for A, and rotate in the anti-clockwise sense, because our value sign for this moment is positive, so rotate in a anti-clockwise sense, arrow coming toward, after one rotation, arrow coming toward the left hand side, so show toward the left, this 24.44. Then for 26.58 kilonewton moment at the end, the sign is minus, so you have to rotate about B in a clockwise sense. After one rotation, arrow coming toward the left hand side, so 26.58 show toward the left hand side, and after that you join this, you will get the bending moment diagram for the end moment. Then the next is a BC beam. The value is 26.58 kilonewton meter for B, and the sign is positive, so you have to keep your pen over the close to B or the BC and rotate in anti-clockwise sense. After one rotation, arrow coming up, so show up, and at the C there is a hinge support, so it will be, moment will be 0, so you will get in a triangular fashion. Then draw the free bending moment diagram for the load. Here is a UDL 25 kilonewton per meter, so the equation or formula is WL square by 8, you have 28.125 kilonewton meter. And for the point load 50 kilonewton, let's draw the free bending moment diagram, WL by 4 in a triangular fashion, you having a 50 kilonewton meter. So this is our superimposed bending moment diagram. Okay, thank you.